much. Today is the first public outing of APLX version 5. You should all have a copy of it on your USB sticks, which came with the conference, so I hope you'll feel free during the conference to just have a play and kick the tyres. And if you've got any questions, please come and grab me during the conference, and happy to explain anything. Richard Navavi will be talking about APLX version 5 tomorrow and showing some of the new features. But today I'm just going to concentrate on one thing, which is the interface between APL and the R Statistics package. You may be thinking that APLX version 5 looks disappointingly like APLX version 4, by the way, but all the good stuff comes tomorrow, the visual stuff. Slightly drawn from a short straw, because I've got to stand up straight away and say that I am not a statistician, and I'm quite aware that sitting here there may well be some people who are expert statisticians. So for the actual statistics content, I apologise. If you don't know R at all, it's two things really. It's a computing language in its own right, an array language. But the reason that an APL programmer is interested in it is it's also a huge library of statistical functions. If you want to do linear regression, if you want to do classical statistical tests, analysis of variance, cluster analysis, there are thousands of functions which are available to the APL programmer. And I think Morton made a very good point this morning, which is there's a lot of code out there which is not necessarily written in APL, a lot of Java code, a lot of .NET code, a lot of R code, but which can be used from APL very easily. And so a lot of the focus of what we've done with APLX is to make it as easy as possible to use some of that. R is a GNU project. It's a free software and fairly easy install, so I'd encourage you to just download it off the R website and have a play. What I'm planning to do today is I thought we'd get straight in and just have a look at calling R from APL, just to see why you might want to do it. We'll back off and just look a little bit at the R language itself, and then we'll finish up coming back to APL and understand how the interface between APLX and R works. So let's get straight in. I was looking around for some sample data, and I was very pleased with something that I found. So a place I've always wanted to go to is Yellowstone National Park, and of course the reason to go to Yellowstone is Yogi Bear and the Old Faithful geezer. Got a photo of Old Faithful doing his stuff. Every 45 to 90 minutes, Old Faithful erupts, and the eruptions throw boiling water nearly 200 feet in the air sometimes, and last for about 5 minutes. And of course you can imagine people have done a lot of statistical analysis of why Old Faithful does its stuff, and seeing what they can work out. So I thought we'd just have a quick look at doing it ourselves. So Morton showed creating some objects using quad new. In APLX there's a left-hand argument which is the language which we want to talk to. So that might be Java or Ruby, .NET, or in this case R. And what we're doing is we're loading a plugin which is going to enable us to talk to the R Statistics package. So all that is an APL variable which is a reference to the R language, and in fact it's that particular version. Now the thing about R is it does come with this huge statistics package. I don't even understand what a lot of it does, never mind being able to apply it, but obviously some people will be able to. This is just a list of some of the classical statistics tests in the base package. This is a fraction of it. And we can get all of that from APL. If I just ask the R plugin for a list of the functions which I can call, over 2,000 functions. We just briefly bring them up in the editor window, and you can see the description of how to call all of them. And that's just the base package that comes with R. There are a lot of other packages called particular statistical tests, even things which third parties have written, which you can download to do particular work. So here's just a list of some of the packages which came by default on the R installation. So if we start bringing these in, we will have thousands more functions available. Now the statistics for the old faithful eruptions we can get at. It's a complex, or perhaps I should say a composite R data type called a data frame, which we can inspect from APL. And all it is a two-column table with a list of the duration of the eruptions of Old Faithful in minutes, and then the waiting times in minutes between eruptions. Now I can get those values into APL. I'm just going to read the eruptions column there. Oops. So we've got the data into APL, and we can do simple, we can call the R package to do some very simple statistics, like find the mean of the data and the summary of the data, which is perhaps a little bit more obvious if I display it with some headings. So the minimum, maximum value, the quartiles. Let's just put that, what's now APL data, let's put it back across into the R world and ask R to plot us a histogram of it. So what you can see here is the pattern of eruptions of Old Faithful. It either tends to blow its top for about 2 minutes, or if it does go on, it goes on to 4 or 5 minutes. And we can just add to that the probability density function, just an estimate. Very quickly, we're just asking R to do this, don't need to worry about the details, but... And we look at this bit and say, oh, if we look at the data beyond 3 minutes, it looks a bit like a normal distribution, so let's just use R to test whether that's a normal distribution or not. This is where I'm at the limit of my comfort with statistics. There's a thing called the Kolmogorov-Smirnov test, which sounds like something we should be ordering in the bar later. But it's a test to find out whether some actual observed data fits with a theoretical distribution which you're predicting. So we're predicting a normal distribution of this data. We want to apply the test to it, the Kolmogorov-Smirnov test. So we just use APL to get the eruptions which lasted at least 3 minutes, put them across the R side as a variable called long, apply the, I'm not sure I can say it 3 times, the Kolmogorov-Smirnov test, and that's returned to us actually a reference to some R data, which we can just get the summary of. So our null hypothesis was that it's a normal distribution, and the result of the test is not enough. We can't reject that hypothesis because that probability is not a very small number. That's the summary of it, and of course we can also get the actual values of the data. So that's just an idea of why you might want to do this, and a quick view of how it works. I'm just going to turn to the R language itself for a bit now. And if I bring up an R interpreter, just trying to make this visible at the back. How's that? So it's an interpreter. It's also an array language. This is the equivalent of monadic iota, which they've taken slightly further than APL because you can do things like 10 down to 3. And of course, add a scalar to a vector. You can assign, as you would naturally hope, you can assign to a variable. But notice the rather clunky assignment arrow. We don't have the beautiful APL symbols anymore. And there are a few built-in functions using the symbols like plus and times. But for everything else, we are looking at using named functions. So the sum of x, or the outer product of x with itself, using times. Notice, by the way, that that is in column major order. So any APL interface has got to take care of automatically converting that to what we might naturally expect the data to be. You can have mixed arrays. Sorry, I should say one other thing first, which is you might expect to be able to do this. But it doesn't let you. You actually have to construct a list using a function called C. And you can have mixed arrays as well. And higher order matrices.
Are they mixed or are they all characters there?
No, that is mixed, although it's showing it in quotes.
Okay.
Yeah, X or 1 or quote 1 quote over the show.
I don't know.
I think that's only made into strings.
Oh, is it made into strings?
Lots of strange rules, but there are genuinely mixed arrays in that one, actually, I think.
You're right, I probably have to create a list object rather than just concatenated it there. I think it has done a type conversion, so I believe I could do.
It's easy to make now.
Yes.
Do you know why that made it column major rather than major?
The only reason that I can think, I don't know, is the answer, is when you come to put together slightly higher data structures, like the data frame, it's more natural to read the data down the columns. So when you're converting between different types. But I don't know the answer to that.
I think it might be a Fortran data.
Oh, it's a legacy thing, yeah, quite possibly.
Past keeps coming back out.
So you can have higher order things like matrices, as you'd expect. But you miss APL's elegant way of constructing these things. One very strange thing, strange to my way of thinking, about the R language, because I think in general it's quite well thought through, but there's no concept of a scalar. So if we do the length of 1 to 10 is 10, as you might expect, but the length of 1, 2, 3 is 1. It's a one-element vector. R does have complex number support. But again, I find it's not, I don't know if it's very well thought through, because wouldn't you expect to be able to do the square root of -1 and get a complex number? You actually get not a number, and if we want the square root of -1, I've actually got to ask it as square root of -1 plus 0i. But one thing that I really do like about R, and I think maybe NARS should consider this, is it has the concept of a not a number. A not available. So you've got some data, and we'll be looking at some data later where it's some climate data from the 1850s onwards, and of course there's this very patchy record. And so we've got the idea of not available, which you can actually enter just as NA. And if it participates in any sort of mathematics, 2 plus NA, the answer is not available. If we try to find the sum of that, then again, of course, the answer is not available because there's one value not known. If we do want to find...
Does it equal, is NA equal NA?
Yes, there's a single number, token, object to represent NA.
What is 3 equals NA?
3 equals NA? We're going to some uncharted territory now. Oh, sorry, it's not equals, is it? You remember the R for equals? Equal? Any R experts here? Yes, there we are. Equals NA. If we do want to get the sum of the vector there which contains not available, we can actually do it by Now the reason that I really wanted to show you that is just to make the point that R calls can take a keyword, and it's specifying, telling which parameter you're specifying, and it's actually one of the things which is the biggest problem when calling it from APL, is we can't easily feed keywords in to be able to do that sort of thing. Just to quickly look at a higher data type, if we just assign 2 variables, and make a thing called a data frame. Now you can see from that one that the data frame has got our values in the columns, but it's also got some column headings. And the way this works is that our data can have additional data called attributes attached to it. There's nothing special about an attribute. You can attach a character attribute or some more numeric data. If I just show you the attributes for that data frame, you can see it's got an attribute called names, which is the names of the columns, and one for the names of the rows, and then a class attribute, which we just see mentally mentally note the class attribute. We'll see it again in a minute. One of the great things about R as a teaching tool is that it comes with a lot of statistics already provided. So if you want the results of the classic Michelson-Morley speed of light experiments, or I saw the last survivor of the Titanic died just recently, and they give you the survival rates for the Titanic as built-in data. They're obviously good for teaching. I'm just going to use it to plot that. What you can see there is your worst chance of surviving really is if you were a male crew member, then you were most likely to go down with the ship. Or there's some sample data which is carbon dioxide measurements from, I think, 1959 through to about 1990 something, month by month. It's actually a time series. And again, if I just plot it, you can see that we very quickly get able to get a plot of the time series. Or we just do a seasonal decomposition of that, because that was month by month data. And we get a completely different graph up. But we're just using the plot function every time. And so you may be thinking, well, how does it know how to do that? And the answer is that class attribute. It's just a character string which is attached to the data. So Titanic is a data type table. The CO2 carbon dioxide data is a time series. And finally the seasonal decomposition one. So I hope that's just a little bit of an insight into the R language, which we can now use to go back and look at it from APL with a bit more understanding. Morton has done a little bit of my work for me by showing one way of calling R, which is based on Professor Alexander Skomorokov's work, Sasha. And what he did was basically wrote 4 functions which allow Dyalog APL or previous versions of APLX to talk to the R package through the COM interface. So, very simple to use, just initialize it. We can put a variable across into the R world, so we're creating an R variable called X with some data. And naturally we can get it back again. And we can call functions in the R world and ask them to return results to APL. And you can even take it as far as doing some plotting. But what we've done with APLX version 5 is to just take that as our inspiration, but try to integrate it much more tightly into APL. In the same way that you can call Java or .NET or Ruby from APLX, you can also call R in a hopefully a slightly more elegant way. So the equivalent of Sasha's R put is we just assign a variable directly into the R world, and the equivalent of R get is we just grab it back again. And we can call it. Sasha's R exec is quad eval. and we can plot. So we've got the same functionality there, but we can take it to a higher level. The first thing we can do is, there's no need to assign any data across. We can just directly call an R method mean on some APL data, and we can directly plot some APL data. In the example with mean, you may have noticed that I had to enclose the argument to mean, and the reason is that the mean function is expecting a single argument. It can then take additional keyword arguments, but here's an example of calling the function called outer, the R function, with 3 arguments. You remember the carbon dioxide data? I want to say something now about boxing and unboxing, which is a term which may be familiar to you if you've used languages like Java. For simple data, just simple numeric arrays and vectors and character strings, by default, the APLX interface will automatically unbox the data. So, as we saw, we assigned to X, we got back a numeric vector straight away. For something like a time series, this carbon dioxide data, by default what happens is that it returns an object reference to APL, which we can then use to do further things with it. So we can use quad val to pull out the actual numeric values of the carbon dioxide, and there's rather a lot of them, so just the first few. Or if I just assign that reference to an APL variable now, I can call an R method called summary on it, and that gives us the data for the range and the quartiles and the mean. And the reason that works, I'm not having to type r.summary CO2, I'm actually just typing CO2.summary, because we've just added a little bit of syntactic sugar, which is that if you type obj.function with some arguments, it's just equivalent to typing r.function obj arguments. It just makes for a slightly cleaner interface, more readable. How am I doing for time, Bradley? Oh, right. Might have better. Similarly with ordinary data, we can leave it boxed up and directly call it. But let's just turn to something a little bit more interesting, which is I'm going to use R now to do some 3-dimensional plotting. APLX has got built-in 2-dimensional charting, but the 3-dimensional stuff in R is excellent. So here's a little demo, which is APLX calling R. APL is managing the window here, all of the scroll bars and that sort of thing, but it's calling R to actually do a plot. And so I can use the scroll bars to change the viewing angle of this data. And if I just quickly pop up the function to do it, you can see that we've created a little bit of data to plot, and I used a mixture of R and APL to do that. Create the window entirely in APL with some scroll bars which are controlling the viewing angle. And then we're using another function to actually do the 3D plot. And what we're actually doing here is we are calling an R function to do a perspective plot and writing it in fact to a bitmap. Rather than charting it directly to an R graphics window, we're writing it to a bitmap and finally sucking the bitmap back into APL and displaying it in our APL window. APLX doesn't have complex number support, but we get it for free by piggybacking on R. So we can now have a complex number for which we can display it or get the real and imaginary values. And you can also create complex numbers. Oops. Also the square root, and you can even create a whole array of complex numbers all in one hit. Just ask for real and imaginary values, square root. You remember the data not available? We have supported it to some extent in APL, that we can recognize that a value is not available. And you can create your own one in APL. Now you can't do something like free plus not available in APL. It's a domain error rather than integrate it into the language. It'd perhaps be nice to do at another step. And I think if Mars wanted to do it, it would be a fine thing.
What is free plus
We're in APL, so free plus NA is just they're not equal. One's an object reference and one is a scalar integer. So. And so we can. This is APL data, which is including that not available, and we can try summing it, and we get the answer back not available. Or we can. You remember I said that some routines take keywords, and so we have to put the data across into the R side. If we want to supply a keyword argument, we've got to use quad eval. We put the data over onto the R side, and we can get the answer back. Or, of course, we could use APL.
The value you're assigning to NA, you're saying that NA should be treated as 0, or what is that, RM?
It's like here.
The eval, quad eval.
NA.rm equals true. That's on the R side of the world. What it means is remove not availables from the thing before summing it. Yeah. I just want to very quickly say something about attributes. So we can create a time series of APL data, and we can examine its attributes. And we've also given you a way of very easily getting at the attributes from APLX, or indeed changing them, which is just using the delta rather. So the time series here is a series of 10 values with a frequency of 1. But you can change it, so we say, okay, it's data from 2000 to 2009, and it's yearly data. And we can also assign our own attributes. There's nothing special about an attribute, it's just extra data associated with an item. So you can see I've changed it. I just want to wrap up, just showing you a real application. How am I doing for time, Paul?
You've got 5 minutes.
5 minutes.
Just over 5 minutes.
It's going to work. It's going to work. I wanted to get hold of some real data just to have a play with it myself, really. I've been reading a very interesting book on climate change. So I've got some temperature data from the Climate Research Unit at the University of East Anglia. This is their webpage, and I thought it would be fun to just have a go at reproducing that graph. And so all the data is available on their website, and in particular I'm using a data file of monthly temperatures taken all over the globe. They divide the globe up into 5-degree latitude by 5-degree longitude squares. Take the monthly temperature from the 1850s up to the present day. So, of course, you can imagine that the ships didn't go everywhere in 1850, a lot of not available data. And it's in a format called Netcdf, which is a text file format, but with a rather special format. We could unpick it in APL, but I'm going to actually just get R to unpick it for us. I'm not a climate scientist, so I was slightly horrified to find out that Reading University just near here are all experts on climate science. I hope there's no one watching. So there are a lot of additional packages which are not part of the base installation of R, but where people have written extra stuff that we can use from APL. And I'm going to use a library called the Netcdf Library. Just load it in there. And I'm just going to ask, sorry, I'll read the data. I'm going to get a reference to that data into APL. Let's close the file. Ask for the dimension of the data. Well, it's 5 degree latitude by 5 degree longitude, so it's 72 by 36, and then 1,912 months. Because there's a lot of not availables, I'm just going to ask R to do the averaging for me. So I just put the data back across to R, and I'm going to average for each month of the year across the globe. Now, I'm not sure of the statistical validity of that, but so we've now got the average monthly temperature. 1,912 months since 1850. And we'll create a time series of it. And we say the time series is from 1850 to March 2009. And we'll just get R to plot a seasonal decomposition of that. So you can begin to see the temperature is possibly inching up slightly. Well, how many complete years of data? We've got 159 years of data. So let's just get APL now to compute the average temperature for each year. And then we can say, well, which was the hottest year? And slightly alarmingly, a lot of recent years in the data. Well, let's create a time series just from that yearly data. From 1850 to 2008 in yearly steps. We just summarize the data. We just put it across the R side of the world and plot it. And let's just compute in fact I'll just get APL to do it because we're running out of time. Let's get APL to compute a 9-year moving average of that as well. So we're doing a 9 plus slash on the values in the time series. And mustn't forget that APL can also do sorry, just editing as we go here. Mustn't forget that APL can also do charting. So I'll just get APL to bring up a chart. And so there we've roughly reproduced the Climate Research Unit Hadley Weather Centre chart of the data using a mixture of R and APL. That's basically what I wanted to show you. The message that I suppose I want to leave you with is there's a lot of software out there. We don't need to keep reinventing wheels. There have been APL attempts at doing statistics libraries, and quite good attempts, but R is so comprehensive that rather than trying to write it again in APL, let's just make it easy to call R, and equally Java, .NET, Ruby, and we've got someone working on a Python interface, a customer of ours. Let's make APL play as well as we can with the other languages. It echoes very much what Morten said. So thank you very much.